Artificial intelligence is making decisions all around us, from what we see in our social feeds to how our loans are approved. But here's the question: do we really understand how these decisions are made? That's where explainable AI comes in. AI and ML systems are only as good as the data we provide them. Even the best AI systems will fail spectacularly if the data that you're providing is incorrect. And that can be due to many things like biases, noise, inaccuracies with the dataset. There have been many examples of this that have made the news. The first example is an AI recruiter that was used at a very popular company where they didn't use representative data. In this case, all the resumes within their dataset happened to be from mostly male candidates. This recruiting system was used to select potential candidates to advance to the next round for interviews. Another such example is when lawyers used an AI system to help them argue court cases. The arguments, and more specifically, the court cases the AI systems provided, were hallucinated and never existed. So what is explainable AI? Explainable AI refers to techniques and methods that make AI models' decisions transparent, understandable, and interpretable. Explainable AI is about peeling back the layers of our models to understand not just the decisions that they make, but why they make them. It addresses the black box problem, where AI makes predictions without explaining the reasoning. So why does this matter? There are several key reasons. The first, trust and transparency. When users, stakeholders, and regulators can see how decisions are being made, it builds confidence in the AI systems. Transparency fosters trust. Next, debugging and model improvement. Explainable AI helps us uncover hidden biases, inconsistencies, and data quality issues. By understanding the decision-making process, we can better diagnose and improve our models. Finally, compliance and ethics. In industries like healthcare, finance, and legal, where decisions can significantly impact lives, it's essential that AI systems are not only effective, but also ethical and compliant with regulations. The key goals of explainable AI: interpretability. Our aim is for humans to clearly understand why a model made a specific prediction. Accountability. AI systems need to provide solid justifications for their outputs, ensuring that decisions can be scrutinized and trusted. Fairness and bias detection. By revealing how decisions are made, explainable AI plays a critical role in detecting and mitigating biases within datasets and models. Explainable AI isn't just about making technical processes transparent. It's about ensuring that AI systems are understandable, fair, and trustworthy for real-world applications. AI models are only as good as the data they learn from. But what happens when that data is flawed? When we talk about AI making decisions, we often assume it operates in a purely logical and objective way. But in reality, AI is only as good as the data it learns from, and that data isn't always perfect. AI decision-making is directly shaped by the data. Every model's prediction and outputs are based on patterns it finds in training data. If that data has issues, those problems will reflect in the model's decisions. There are numerous issues that can arise when training AI and ML models. Things like annotation errors, data biases, distribution drift, adversarial inputs are all at the top of that list. Even a well-designed AI can have unintended consequences. AI models are great at optimizing for patterns, but they don't understand the real-world effects of their decisions. Now let's take a closer look at 4 of the most common of these issues, how they happen, why they matter, and what we can do about them. What you see here is a simple yet powerful example. The dot is clearly green, but it's labeled as red. At first glance, this might seem like an obvious mistake, but in real-world datasets, these kinds of errors are much more common and often go unnoticed. Now, how do these annotation errors occur? There are 3 primary causes. First, human mistakes. Labeling is typically done manually and oftentimes by individuals or companies in other parts of the world that might not have full understanding of how to label your data. The sheer volume of data makes it easy for mistakes to slip through. Ambiguous data. Sometimes the data itself isn't clear. A data point might not have an obvious or correct label, leading to inconsistencies that vary from one annotation to another. And finally, automation issues. When labels are generated through automated processes, an error in the algorithm can quickly propagate across the entire dataset, magnifying the problem. The impact of these errors on AI models is significant. Even a small percentage of annotation errors can compromise the integrity of an AI system, underscoring the need for robust quality control and explainability tools. AI models learn patterns from the data they're given. But what happens if those patterns actually reflect societal biases rather than objective reality? Researchers at Princeton set out to explore this issue by developing a tool specifically designed to analyze biases in computer vision models. In their study, they focused on how AI detects people and a musical instrument, in this case, the organ. For clarity, they highlighted people with red boxes and the organ with blue boxes. One of the key findings was quite revealing. The AI inferred 3D distances between people and the organ to determine their relationship. What they discovered was that males were predominantly shown as actively playing the instrument, whereas females were often depicted simply as being nearby, without any active interaction. This discrepancy suggests that a model's training data contain patterns that mirror societal stereotypes, and these biases can have far-reaching effects, not just on object detection, but also downstream applications like automated content tagging, hiring systems, and even AI-generated media. The takeaway message here is clear. Data bias isn't always obvious at first glance, and depending on the system, can cause significant harm, like in the AI recruiter example. Let's talk about a fundamental issue in AI training: data imbalance. Imagine a simple data set with two categories, cats and dogs. In our example, there are plenty of cat images, but only one dog image. This imbalance means that our model can become heavily biased towards cats. Because the model sees so many cat images, and hardly any dog images, it tends to predict cat most of the time. In extreme cases, the model might completely ignore the dog category. This problem isn't just theoretical. In healthcare, underrepresented demographics in medical datasets can lead to misdiagnosis. Similarly, facial recognition systems often perform poorly on darker-skinned faces when the training data is dominated by lighter-skinned individuals. We should strive to build more representative models that perform fairly across all classifications. A distribution shift happens when the data your model sees during deployment is different from the data that it was trained on. This misalignment can lead to degraded performance and unexpected failures. Here, the top set of images show a classifier that was trained on real-world photos of cats and dogs. In contrast, the bottom set displays cartoon images. While we can easily recognize both, the model might struggle with cartoons because it would never learn those features during training. This occurs because the model has picked up on specific visual patterns, like textures, lighting, and color gradient, from real photos. It may even rely on background details that aren't present in the cartoon images, leading to misclassifications. Real-world examples further highlight this issue. A medical AI model trained on high-resolution scans from one hospital might underperform on lower-resolution scans from another. Understanding these shifts is crucial for developing robust AI systems that can adapt to varied real-world conditions. Now let's talk about adversarial samples. These are inputs like images, audio, or text that have been slightly altered in ways almost invisible to the human eye. Yet, they cause AI models to completely misinterpret the data. A common method to create these samples is called FGSM, or Fast Gradient Sign Method, developed by Ian Goodfellow. Instead of tweaking the model's internal parameters to improve accuracy, FGSM makes calculated tiny changes directly to the input data. It essentially uses the same gradients that help a model learn, but in reverse, to confuse the model. A classic example of this is the panda image that, after applying FGSM, is misclassified as a given. This highlights how a minor change can lead to major misclassification, showing the vulnerability of AI models to adversarial attacks. I want to quickly highlight some fantastic tools that can be used for explainable AI. Captum is a great tool which is a part of the PyTorch ecosystem. There's SHAP, which offers robust model interpretation techniques. Next is Lime, a tool that helps us understand individual predictions by approximating complex models locally. There are a variety of open source tooling available. I'd strongly recommend taking a look at each of these tools and finding one that fits your particular use case. I hope you enjoyed this discussion on explainable AI. Thanks for watching.